Good? Okay. All right, let's get started. So we began the topic of failure detection in the last class, and I mentioned to you that this is a substantial topic. It's going to take us many lectures to get through, unpack the whole concepts, learn about the different techniques, so it's quite a big subject. But we have to start somewhere. Yeah? Can we continue? Okay, thank you. We have to start somewhere, and the first step is detecting a failure, because if you can't detect a failure, well, you aren't going to be able to handle it. Now, on the face of it, this sounds pretty trivial. How hard can it be to detect failures, right? Hold that thought. It turns out that there are two very different kinds of failures. One class of failures are transient failures. You look now, and the failure is there. You look again, and the failure is gone. You have seen one example of this in the first half of the course. What's that example? Any volunteers? Yeah? Oh, you're just touching your mask. I thought you had an answer. Okay. Any suggestions? You've already seen this, yeah?
Just like in the, you send a message and it's like 50.
What's that?
You send a message so it's like 50.
Something even more basic. Packet loss, right? You transmit a packet now and it's lost. A few hundred milliseconds later and it works. This is the whole point about retry. If it wasn't true, what's the point in retrying? Right? So, transient failures are failures that occur under some combination of unlikely circumstances. Now, packet loss happens to be one that we anticipate, but there are many others, like deadlocks, which you learned about in 15.2.13. Right? When you have concurrency control, when you use mutexes, a very simple example is if you have A and B as two different mutexes, process A or thread A asks for A and then B, some other process asks for B first and then A, and if the first request of each succeeds, they will be deadlocked forever. You randomly throw a dice and re-execute, and the scheduler picks different choices. This time it works fine. And the reason is because there was no context switch between the first request and the second request, right? So real systems of this kind, who knows? There are countless decisions about the scheduler, about the slight delay in your packet getting to the destination. You try again, all those countless little variables are different, and so the outcome is also different. So transient failures are ones in which undoing and retrying has a high chance of succeeding. So in the case of a deadlock, you can kill both processes, start them again, assuming they haven't done anything significant that needs to be undone, and then this time it might work. All of retransmission, which you learned about in the first half, works on this basis. You sleep for a random amount of time, you retry, this time it might work. Okay? So this whole area is actually a very important part of distributed systems. Notice this point here about undoing. It's actually important. The case of packet transmission is trivial because you have attached sequence numbers. The act of undoing a previous transmission is trivial because at the destination, duplicate elimination effectively achieves that goal. So there's no actual work that you have to do at the transmission point. It's at the reception point that you have to do the undo. But in some sense, the higher level point is still true, namely redoing the operation works. Then there's a completely different kind of failure. If your neighbor is having work done on his house and the backhoe cuts the Fios cable to your apartment, no amount of packet retransmission is going to help. They're all going to be lost. Similarly, if a server dies, the machine room is flooded, etc., 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 the disk crashes. So those kinds of failures are referred to as persistent failures. That failure is not going to go away on its own. Retrying, randomization does not help. There's going to have to be some action which is referred to as repair, like somebody coming, digging a trench, finding the Fios cable, replacing it. That's a lot of work. Okay? That has to be done before this can be fixed. So in our work, in the lectures moving forward, we're going to consider both kinds, because both are real, both happen, and how you deal with them, sometimes the same techniques work, other times you have to think differently. So we'll see how all that works. Now, in the case of persistent failures, you can ask the question, how frequently does it happen? How frequent is it that my neighbor has work done and the repairman break my cable? Hopefully, it's an extremely rare event. Hopefully, many workmen come to my neighbor, get work done, they don't break the cable. It's just truly a rare event, right? So, if you look at your Fios cable to your home, it's working for days, weeks, months, maybe years. Nothing's wrong with it. And then one fine day, Murphy strikes. Your neighbor's workmen cut the cable. You call Verizon, they schedule it. They schedule the visit for 2 days later. Eventually the guys show up. They diagnose the failure. They say, oh, it's going to take another week before the workmen can come and dig a trench and put a new cable in. So this period of time is now many days, because your internet connection doesn't work until then. Then finally, it starts working until the next big disaster happens. This time it's not workmen, maybe it's a drunk driver who rams into the lamppost that has the Fios cable coming to your neighborhood. Now it's not just you, but you and all your neighbors who have no internet service. Hopefully Verizon fixes that one faster, and so you get going again until the next failure. So if I just look at that Fios cable or the Fios service, you have periods when it's working perfectly, the blue periods, and then periods when it's not working. And retransmission doesn't help in these, or retrying doesn't help in these red pieces. Now you can view each of these as a random variable, and each of these to have a random distribution. So from the blue distribution, I have 3 samples. From the red distribution, I have 2 samples. The assumption is that the kind of phenomena that result in failure are different from the kind of phenomena needed to fix the failure. And so if you treat these as 2 different random distributions, It depends on the shape of the distribution, how many parameters you need to characterize it, but all of them, no matter how complicated the distribution is, at least have a mean, right? The very least. That's the first moment of the distribution. And so the mean of that distribution is referred to as the mean time between failures. Okay? And the mean of the other distribution, of the red distribution, is referred to as the mean time to repair. So these two variables characterize the universe in which you are operating. Every service that you use, Google's cloud computing service, if you depend on Google Maps for navigation, there is some non-zero likelihood that when you try to reach it, it doesn't respond. Maybe the machine room had some big problem, or the server died, or there was a new release of Google Maps that has a bug that afflicts your Android client. Who knows, right? The reasons may be many. But the point is, the service is not working for you. Hopefully, in a well-built, well-engineered distributed system, the mean time between failure of the service is very long. Hopefully once in every few years, right? Because if you're going to depend on this thing for navigation, it had better work almost always, right? So these are distributions that characterize individual components, hardware and software, and infrastructure and operators, right? All the components involved. And they also characterize the higher level service that is built out of them. And good design, which is the focus of this course, is given individual components that have these patterns, how do I build a distributed system in which the blue part is incredibly long and the red part is incredibly short? If that is the case, then you have built a distributed system that is up almost always, and when it's down, it's only down for very short periods of time. Ideally, you'd like the red part to be zero. No system made by man can achieve that. Coming close is the best we can hope to do. Yeah?
Are we assuming that each small part fails, then that means the entire service fails?
That depends on how you've designed the system. When you transmitted a packet, if one packet got lost, did the whole transfer die? No. But that's only because you had the foresight to put into place the expectation that this might happen, the mechanisms needed to cope with it, including timeout, retransmission, and you had included in the packet sequence number to perform duplicate elimination. That's my point, that with sufficient foresight and careful engineering of the distributed system, you can achieve a system-level blue that is much better than individual components blue. And that is what this whole second half of the course is about. Any other questions? Okay? Keep in mind something, very important point, and in fact you'll actually experience this. Everything I told you about treating these as random variables, right? If you go back to your elementary probability and statistics, okay, you need independence of phenomena, right? The typical term is IIDV, independent, identically distributed variables, right? That's the basic assumption. Now, when it comes to things like the FiOS cable the drunk driver hitting the lamppost, the workman chopping the cable, it's probably true. These are truly random events. But notice, it doesn't apply to something that you work on every day. Very often, it doesn't apply to software. Because if I put a new release of the software on 10 servers, the same bug can strike all of them, depending on what the bug is. So in reasoning, you have to look very carefully at the details. If an incoming packet arrives at a server and tickles a bug, it's quite possible that sending that same packet to another server will kill that server also. And then you send it to the next one, and that dies too. There's no independence here. It's deterministic because of the bug that you have in the code that this failure will happen with 100% likelihood. It's not probabilistic. So in reasoning, you have to look very carefully to see whether the bug in question is deterministic or if it's a probabilistic bug. And some of the biggest sources of errors in the distribution, in the implementation of distributed systems arises because the designer doesn't realize that he or she has introduced a deterministic source of failure and thinks that in fact failures are independent. They do not realize that there's a component that is common to all of these systems that can fail. Some of the same reasoning also applies to security vulnerabilities. Okay? Very similar reasoning. You can either think of it as Murphy being evil or Murphy being mischievous. Murphy is mischievous, it's failures. If Murphy is truly evil, then it's an attack or security vulnerability. But the reasoning is very, very similar. Any questions before we move on? Yes?
How about transient failures that are like somewhat likely to happen, like happens a quarter of the time, half the time, or whatever?
Not sure I understand the question. Ask it again.
So transient failures are very unlikely. What would you like not always doesn't happen every time and can be retried, but it happens like half the time or whatever. Like every 2 failures.
Well, then it's a transient failure with a high probability P. Okay? But there is a big difference between that and a bug in which your packet, when it's processed by the C code, every single incoming packet with this value of X results in a null pointer dereferencing. The server is going to die. That's deterministic. That's deterministic if you fix the incoming packet value. If you pick random incoming packet values, then the failure looks as if it is probabilistic, because not every packet contains the same incoming parameters. Yeah. So part of debugging involves narrowing the failure case down so much that what was a transient failure now appears to be persistent. Once you've done that, you've effectively found the bug, or at least come closer to finding the bug. Okay? Good question. Any other questions? Okay. So, one of the most insightful empirical sources of data about failures is from long ago. Okay? It dates back, how many years ago is that? 47 years ago? 37 years ago. Right? Long time ago. You may ask, okay, how can this be? We've had so much more computing since then. The answer is, this information is considered top secret. If you're a service provider, Amazon or Google or Microsoft Azure, you don't want to release these figures. Your competition may use it against you. In a world of litigation, every time you admit to a failure, there's some lawyer out there who's going to use it to say you were negligent and sue you. So, in practice, in today's systems, it's extraordinarily difficult to get accurate information about actual failures, where they occurred, why they occurred, etc. Okay? We were fortunate that this data was published before a lot of these things became so substantial. This is still a useful source of information. So this is in your optional reading. Okay? If you'd like to take a look at it, please go ahead. Let me summarize for you what that study says. So Tandem, as the name implies, was a very early system built to be highly reliable. It had dual processors, dual buses, dual disks, and software to make sure that in case of a failure, within a few hundred milliseconds, the components which were supposed to take over in case of failure would kick in, and you, the user, would not even see the difference. So think about it. This is 1985. It was all mainframes, right? Because the personal computer had only appeared in 1981. The web did not appear for another 10 years. So this is mainframes. In that era, in that world, this was a very specialized mainframe which was used by banks and other high availability applications. It was very expensive hardware. Mainframes were expensive. These were even more expensive. So the data that is provided is only on persistent failures. There's no data on transient failures in this study. Okay? Also, keep in mind, because the system was by design a high availability system, the expectation is that the code quality was very good, was much higher than the random web service that you find today. So you should treat what is learned from here as a kind of a lower bound on the kind of likely failures in a real system. Okay? So they observed over 7 months in 2,000 customer sites. Right? That's how many were deployed. So this is data over that period of time, over that many systems. This is a non-trivial empirical source of data. Close to half, 42% of the failures were caused by human error. Almost half. Okay, and I'm not including here software bugs by developers. This is the operator whose job it is to maybe add a new user, add a new disk, maybe configure something. Human error accounted for nearly half, 42% of the failures. Next, most important, was software bugs. A quarter of the bugs were software bugs. And then hardware hardly ever failed. And then everything else, environment, all the stuff. So if you look on the right side, you see the mean time between failures if you model this as random variables. Yes?
How can the failure time be so long?
They don't add up to 100%. Yeah, it'll be slightly more than 100% because of rounding errors in the data. What's that?
The computer was interacting like.
I'm sorry, I don't understand the question.
I mean, why the time is so long? the research is down 30 years ago. How can the time be like?
Oh, these are estimated values, right? You basically see how frequently they occur and then extrapolate to the components. So they're not actually, nobody sat around for 87 years, okay? Remember, you are accelerating, because there are 2,000 tandem systems, okay? You are conducting an experiment 2,000 times faster than real time. On one system, the likelihood is 87 years for this kind of failure. That's the reason why you're even able to, but it's a good, excellent question, by the way. The only reason is because this is merged data from 2000. So you can do the math to see how long, to get 87 years, it's 87 divided by 2000, should have been the inter-failure time across in the merged data. Okay, any other questions? Yeah?
Why does maintenance time failure? That just sounds like they shut the server down for repairs. Why would that be punished as a failure?
You mean which one?
In administration maintenance.
Oh.
Sounds like they add repairs.
Well, if they just shut it down for maintenance, that's not considered a failure. But if they're supposed to add a new user and they mess up, and as a result the system is unavailable to anybody for 12 hours, that is an error directly attributable to administrative error.
Yeah.
That's what that is referring to. Okay? So this is quite eye-opening between human error in administration and software bugs, which are caused by software developers. That's almost 2/3 of all failures of system are human in origin. Okay? So this is the point. People are the biggest source of failures. How many of you know this quote about computer man and dog? Nobody? No, the professor has given you this quote in a previous class? Really? You're not pulling my leg? Okay. So there's a long-standing joke in the computer science community about how do you build a reliable computer system? Okay? And the answer is you need 3 components. You need a computer, you need a man or a woman, and a dog. Question is, what is the purpose of the dog? The purpose of the dog is to keep the man or woman away from the computer. All those errors on the previous slide would have gone away, right? If they had only followed this instruction. So keep in mind something. You know, that study that I quoted to you, Jim Gray's study, is pre-internet. The mainframe. Okay? The chances that those failures are increased is actually quite significant, because code today, depending on who's writing the code, you have all experienced code. You look at that code and you say, you know, the guy who wrote this app wouldn't have succeeded in 15440. Right? It's such buggy code. And yet people make money from it. So it's important to also appreciate that many bugs that are classified as operator failure, you can drill deeper and ask, was the operator stupid? Was he or she asleep? How could an intelligent human being who's paid highly, hopefully, to operate the system, how could they make such a stupid error? The answer, in many, many, many cases, is that what is an operator failure is very often because the system is confusing to administer. And so what we call operator failure is actually a usability failure on the part of the designer. Let me give you a trivial example. Many of you drive, perhaps all of you. In modern cars, the gas pedal is to the extreme right, the brake is to the left of it. Imagine you rented a car and the two were reversed. In an emergency, right? I mean, your instincts are to press the brake. And you would step on the gas with disastrous consequences. Now, technically, your insurance company and the police would have no sympathy for you. That would be recorded as operator failure. The driver made a mistake. Instead of stepping on the brake, he stepped on the gas pedal. But let's face it, the real culprit here are the idiots who built that car that way. That's a usability error. Okay? This phenomenon, as I will show you in the next slide, actually is much deeper. Okay? About 20 years ago, 2003, a group of people at Berkeley said, you know, that Jim Gray study was so valuable. In 20 years since then, you know, software programming languages have improved, operating systems have improved, hardware has improved, lots of things have grown better. Why don't we try to redo this kind of study in a modern internet setting? We wonder, with the pattern of failures, what would they look like? Now, you can't exactly replicate the study, obviously, but this paper is also in your optional readings, so feel free to go look at the details. Here's what they did. They looked at 3 internet services. Remember, it's 2003, so the actual study was probably done in 2002, so almost exactly 20 years ago. Okay? They anonymized the names of the companies so they wouldn't get sued. Okay? They called them online, read mostly, and content. So these were 3 different internet services. And these were the statistics that they gave. These are all hits per day, 100 million, and then the content website was pretty low. It's about 500 machines on 2 physical sites, 2,000 machines on 4 sites, 500 machines on 15 sites. So in terms of number of machines, it's at least as large as the original 1985 study. But if you look at number of sites, it's whoops, what happened there? Come back. Okay. If you look at the number of sites, it's certainly only like a modest number of sites. And the total number of failures was much smaller than the original study, but the period of study, they deliberately kept this close to 7 months in one case, close to 6 months in the other. The other one was shorter, 3 months. So this is the background. So what did they find? These are the causes they found. The operator failure was 1/3 of all failures, except in the read mostly case where there was nothing to do. I mean, the data was, fixed. As long as it was running, there was no change, just handing out static data. Second was software failure. 20 years in a world of difference between the two systems, but the origins of failure are quite similar. Right? Quite eye-opening. And this is a very insightful observation that to this day, 2022, human error caused by operational misconfiguration and things continues to be to this day the dominant source of failures. And the second most are bugs in software, which are again a human failure because they are the programmer, not the operator. Okay? So, key observation is that exactly this pattern is noticed not just in distributed systems, but in many other technical systems. So that's a quote from 2016, analyzing nuclear power plant accidents. 3 Mile Island, Fukushima, Chernobyl. Right? Chernobyl is in the headlines again in Ukraine. And a repeated observation is that in all cases, either the designer, in the case of Fukushima, underestimated the potential height to which water could rise in case of a tsunami. And as a result, they did not build high enough walls, retaining walls, to prevent the flooding of the reactors. That was a fundamental trigger that caused the rest of the chain to follow. In the case of Chernobyl and 3 Mile Island, they were both operator errors. A confusing system triggered by an operator who was not quite aware of what he was, I think both cases it was a male operator, so what he was doing and triggered this bug. Another fascinating error is a airliner, passenger airliner. This is quite recent. It's only 7 years ago. So on a flight from Rio de Janeiro in Brazil, to Paris, this big Airbus 330, I think was the aircraft, filled with over 200 passengers, takes off normally, and one instrument happens to be the pitot tube that measures relative airspeed, clogs up with ice. As a result, the instrument errors don't make sense to the pilots. There were 3 of them. Because it was a long flight, there were actually 4, 2 crews. Pilot, co-pilot, and a changeover mid-flight to the other crew. So 4 people, not just one operator, did not know what their altitude was. And every change they made over the course of multiple hours, I think it's 2 hours or so, effectively was lowering the altitude until it literally hit the water from whatever altitude it was at, 35,000 feet. It was pitch dark and night, so they couldn't see anything, but still. Right? This is even more recent, 737 MAX, where effectively an automated component was effectively forcing the pilot to compensate in ways that were totally counter to all their training. And the correct solution was to just turn the thing off, but if you didn't know to do that, you effectively crashed the plane. Right? So that happened not just once, but multiple times. So all 4 of these are technically, it's the fault of the pilot, it's the fault of the operator, right? They are operator error, but one could argue the real deeper failure is a designer's failure that in fact caused this to happen. So you are unlikely to be an operator, but you are very likely to be the designer. So keep this in mind as you design the distributed systems that you work on. How you make the system appear to the operator makes a big difference in their ability. If you switch the equivalent of the gas pedal and the brake, beware of the consequences that you will unleash. Yes?
Are these still considered operator failures?
They're considered pilot failures.
Even in the statistics drawn previously?
Which one?
Similar errors would be considered operator errors.
You mean this?
Yeah, in this and the previous one. My understanding is operators are given a guide and they just have to follow that.
Yes, the guide to your car, this rental car told you, very clearly said the brake pedal is the one on the right. In an emergency, you press the gas pedal.
So a badly designed guide does.
No, the guide is correct. It's a badly designed system.
Okay. So, but it's still considered an
It's
operator.
considered an operator error. We can argue until the cows come home about whether this is fair or not. But the truth is, if you don't want to cause the failure, pay attention to the fact that your operator or the pilot or the driver, in the case of the car, have to make split-second decisions. And very often, they don't have time to go through the entire logic. They almost have to operate on instinct. And making your system work correctly under those conditions is not something most people spend time thinking about. Also remember, the fact that the operator is blamed is unfortunately a very bad incentive. So suppose you're Microsoft or Google or Amazon, and it's going to take a lot of work for somebody to study how people, operators, react under time pressure, and to correctly design the software interface so that the instincts match the behavior of the system. Right? That doesn't happen for free. It's going to take many person months of time and effort. What is the value to Google or Microsoft or Amazon? None. How frequently is this going to happen? Extremely rarely, we hope. And when it does, if the operator messes up, he or she is going to get blamed anyway. So why should I, the software development manager at Google or Microsoft or Amazon, spend time and money now for an eventuality far into the future that may never happen? And even does happen, I don't get blamed. So we reach deep into all kinds of aspects of litigation and law and so on. It's well beyond the scope of the course. But as the one piece of advice I can give you as designers of distributed systems of the future is keep this in mind. How you design your system makes a huge difference to whether these kinds of accidents happen or don't. Okay? All right, so we already covered all this. Okay, so what have we learned about how to build these distributed systems? Number one, that joke about the dog is somewhat true. If you can avoid human intervention, if you can use an algorithm instead of a human, at least you can verify the algorithm offline. The compiler can use strong typing and type checking and all those other things to reduce the chances there are bugs. Moving the source of the error from runtime to compile time helps. Doesn't guarantee that it won't appear, but it helps. So that's certainly one point, which is reduce the number of control knobs in the system. This means now your algorithm has to be perfect, but at least that is being done not under time pressure while the bug or the event is happening in advance. You have the opportunity to think carefully, use tools, verification tools, etc., and hopefully reduce the chances of these automated mechanisms working. Now, unfortunately, it's impossible in systems to have reduce this human aspect to zero. Right? There are always some aspects of a distributed system that involve human judgment, like should I allow this user, should I allow this gentleman over here to be added as a user or not? That decision is not an algorithmic decision. It's a human decision. If he or she is going to be added, what kind of privileges? Should I mark this person as an administrator? Should I mark this person as a user, a developer? Right? Those kinds of questions are not algorithmically determinable. They arise in the day-to-day interactions. So here's another complication. You've all seen on the streets of Pittsburgh the Uber drivers, the Uber vehicles, right? They're driverless. But there's a real person sitting at the controls. That person does nothing. The sole purpose of that person is if the algorithms fail and the car looks like it's going to run into, say, a pedestrian, the human is there and can apply the brakes. So this person's job description is what he or she is getting paid for, is do nothing, let the algorithm run. At runtime, if it appears that the software is not coping correctly, you have to override. Can you imagine how hard it is to do that job? Because it involves doing nothing almost all the time. And then, within a very brief sub-second maybe period, you have to react perfectly. The same phenomena is true for much operational work. You don't touch the system, let it run. If it looks like it's getting in trouble, you better act fast. Most human beings don't work well under those circumstances. And so one of the big challenges, nobody has solved this yet. It's especially true with autonomous vehicles, but it's true in a broader sense. How to achieve this balance between automation and human control, right? How to draw this line and how to do it in a way that is robust and safe is, to this day, 2022, one of the top challenges both in distributed systems and more broadly in computing systems in general. Okay? All right. Now let's look at what can happen when a failure occurs. Turns out there are different kinds of damage, and some kinds of damage are not as bad as others. So one kind of damage can be viewed as data corruption. I transmit a packet somewhere on the internet between here and the Amazon data center. The bits in the packet mutate. How it happens, why it happens, I don't know. But it happens. When that packet lands, it is not the packet that I transmitted. The length is the same, but some of the zeros have become ones, some of the ones have become zeros. Can I tell? Number one. If I can't tell, then I'm going to use that packet. And what that packet says is certainly going to be very different from what I thought I was asking the server to do. So that is a kind of failure that falls into the data corruption category. Believe it or not, this is the easy kind of failure. Okay? This one, it's hard, but we know how to handle it. The much worse failure, much harder failure, we don't know how to handle this well at all, is erroneous computation. You execute on your x86 machine or your ARM processor one instruction. It's got two variables, one in one register, the other register has one, and you say add. And the output it produces is 3. What code will you write to guard against this? How will you write any code to guard against this? Now the good news is many of you in this room who are sophomores have already been programming for what, 4 or 5 years? Maybe you started in high school somewhere. Some of you who are master's students who've worked in industry, you've had many more years of experience, right? Most likely in this entire class, at least the fraction actually in front of me, none of you have ever had to deal with this kind of bug. So that's good news. Very good news. It means, I estimate there are about 70 people in the room. If the average programming experience is for each person on the order of 4 years, that's almost 300 years, person years of programming experience. You have never had to deal. Has anyone actually dealt with this kind of failure? Raise your hand if I'm wrong. You have.
You mean math? No, I didn't math. I was just wondering why the computer computes wrong.
Why is the computer
Wrong, yeah.
Why it computes it wrong? Who knows? I have no idea. I asked it to add 1 and 1 and gave me the answer 3. Right? If he believes this thing will never happen, that's one thing. But the fact is, as I will show you in a second on the next slide, these kinds of bugs do happen. How do you build a system that copes with them? Okay? So, it is true that it's extremely rare. Now, data corruption, as I said, while it's scary sounding and scary looking, is actually the easier one to cope with. And basically, the approach, which we will look at more deeply later, in a later lecture, is the use of checksums. Okay? So it is possible to take a certain amount of data, like a megabyte file, perform a computation on it, and summarize that 1 megabyte in a very short number. That number is called a checksum. So I can take a 1 megabyte file and I can compute using an algorithm called SHA-1. It's a 160-bit long number that summarizes that 1 megabyte file. Now, you know that this is impossible by definition, right? Because the 1 megabyte file has such a larger state space than the 160-bit length. Save this thought for many lectures from now when I'll go deeper into this. Just assume for now that we can do this. That it's possible to get summaries. These summaries are called checksums. Okay? So all I have to do, remember that packet that got corrupted on transmission? So I can send the packet, and at the end of the packet, I can include the checksum of the packet. At the other end, Amazon receives the packet, computes the checksum, computes the checksum of the bits that have arrived, compares it with the checksum at the end, and if they match, then with vanishingly low probability, the packet is corrupted. Okay? The probability is so low that you can consider it to be 0. If there's a mismatch, what should I do with the packet? Just throw it away. Because TCP, or whatever protocol is implementing the reliable transmission, will retransmit. And hopefully the next time around that corruption will not happen. So the ability to use checksums to detect data corruption, and then, there's a huge body of work on how to create checksums, how to make them clever, etc., etc. And there are even flavors of checksums which are able to tell you which bit is wrong and to correct it. Okay? They're called error correction codes. So we'll look at these a little more, many lectures hence, probably in mid-July. But let's proceed with this. How about the second kind of computation? What do I do? Right? very, very difficult. How do I even know the code that is performing the check isn't flaky? If it can get 1 plus 1 wrong, it could get equality comparison wrong. It could get anything wrong, right? So the approach that is used very commonly in aerospace systems, military systems, is an approach called triple modular redundancy. So this dates to the 1960s, okay, when NASA was building flights to the moon and so on, and aerospace systems were becoming increasingly sophisticated. They needed to have reliability. So the basic idea is very simple. You have 3 independent units. They all perform the 1 plus 1 computation. And then you check the bits that come out. If they all match, then the chances are very good, assuming independence of failure, that is a trustable answer. If there's a mismatch, the story gets more interesting. Okay? So I have 3 inputs. I have identical computational units, and I have a voting unit. And if I have one failure, then what I will see, what the voting unit will see, is unit 1 and 2 produce the same bit pattern, but the output of unit 3 looks different. So probabilistically, it is unit 3 that has failed. So I will exclude it. If I get 3 different answers from all 3, I'm totally confused. I don't know what to do. Okay? So you can cope with one failure. Now, on the other hand, suppose these units were built in such a way that they either produce the correct result or they produce no result. Remember, at most once RPC? It had the property that if you ever got a reply back, you were guaranteed it was the correct reply. But sometimes you might not get a reply. You might get a timeout. So suppose these units behaved like that. Then life is a little easier. You can assume that any answer that is actually produced is valid. You can still do checking, but if this doesn't produce any answer and this doesn't produce any answer, and this gives you a bit pattern, you can use that as the bit pattern, right? So these are the kind of reasoning that you can do. However, what does this depend on? Yes? You assume that the voting unit is doing the right thing. Is that the answer you were going to give?
I was going to say the units themselves are correct.
The units themselves?
Because if they're all a false answer, then it's a valid answer, but it's incorrect.
So there are 3 choices, right? There are 2 choices. Either they are not guaranteed to shut up if they don't have the right answer, right? So they're not like at most once RPC. If that's the case, then in fact you need 2 identical results to be able to use the result.
What I'm saying is the software itself that's producing the answer is wrong, and all 3 of them...
Oh, so you're saying that the failure pattern is deterministic. It's buggy software rather than hardware failure. Yeah, then you're out of luck. Okay? This only works if the origin of the failures is truly random. If it's a deterministic failure, it's a good point, by the way. If the reason for the if 1 plus 1 equals 3 is actually just an example of a deep algorithm that you execute and there's a bug in the code and it produces the same answer, the voting will not help. Okay? But if it's really because of random failures, then this approach works. Okay. Notice, as that gentleman over there said, this assumes that the voting mechanism itself is correct. What if the voting mechanism is buggy? So what happens is it can fail in many ways. Instead of taking the 2 correct bit patterns, suppose it takes the 1 wrong one and produces the answer as that. That could be an example of a simple failure on the voter. Now, when there's a real failure, you do not, in fact, mask the failure. You accentuate it in this way. And you can imagine many other failure patterns. So, how do you guarantee that the voting mechanism itself never fails undetected? Well, you could use triple modular redundancy for that. Recursion is wonderful. And so that triple modular redundancy, okay, that one, itself has a voter. How do you make sure that voter doesn't fail? You have one more level of recursion. But you all know that the recursion has to end at some point. So at the very end, somewhere, there has to be one voter, one voting unit, which is not replicated. You trust the answer of it, and that's it. And if it fails, you're dead. Okay? We do not know how to design a system which uses voting that doesn't have such a component. You need that at the end of the recursion. Okay? Any questions? Okay. All so far so good. So, this distinction that I just talked about now brings to us a very important distinction. Components are called fail fast. The same word is also sometimes called fail stop, right? So if you see in a paper fail stop or fail fast, they mean the same thing. I'll use fails fast, but the other word is also used in the literature. So it's hardware software that has a very important property. And this property is exactly what we achieved with at most once RPC. Okay? It's now a generalization of what you already learned. It's hardware software that either gives a correct result with respect to the inputs, or does not give a result. It could be an error code, it could be a timeout, it could be an exception. The details of how it signals, please don't read my output, right? It can vary. So when I do a read system call, I have to check the return code. The commonest source of bugs in the code that you write, you do an open, you don't check the return code. You do a read, you don't check the return code. The bits in the output buffer may not be trusted if the return code said, oh, there was a read error. You asked me to read 1,000 bytes. The first 100 bytes came off the disk just fine. And then there was an unrecoverable disk error. I couldn't read the other 900 bytes. I'm sorry. Now, of course, there's no place in the system that actually gives you this level of detail. All you know is that the return code from the read is minus whatever the errno.h says for IO error. Right? So notice how similar this is to the definition of at most once RPC. So that model, if you're able to achieve, is called fail-fast component. It's a very simple and clean failure model. It says, look, this system is not perfect, may not always be able to give you an answer, but if it ever gives you an answer, you can trust it. That's different from a system which says, you know what? This system always gives you an answer. Sometimes you can trust it. Sometimes you can't. And which one is happening right now? There's no way to tell. It's like a friend. If you have a friend who always tells the truth and occasionally says, hey, I can't share that information with you. That's okay. That's a friend you can deal with. But if you have a friend who randomly tells you the truth and other times lies to you, how do you deal with this person? Right? It's very difficult. It's impossible. Same story here. You want system components that do not lie. That's the goal. Such a system, such a component is referred to as a fail-fast component. Yes?
If they're going to lie to me once every 400 years, like your example earlier, I feel like that might be okay.
A lie once every 400 years is okay. The truth is, yes. The problem is, they're twofold. That number 400 years dealt with one component. The problem is that we are building these systems with hundreds, thousands, millions of components. So that once in 400-year error now is amplified by the fact that there are so many components. And that's the source of our trouble. You're correct, If it's once in every 400 years, and my lifetime is only 100 years, right? I really will not lose sleep. But if my life depends on 10,000 people, and once every 400 years one of them could tell a lie, that lie could happen in my lifetime from that ensemble of people. That's the problem. Okay? Good, very good point. These numbers, very nice, huge numbers like 400-year mean time between failure, does not take into account is each component, of which there are many thousands or millions. And the more complex the distributed system, the more of them there are. And a point you did not ask, but is actually relevant to your question, is where do you draw the boundary of what is a component for which that 400-year period applies? Is it an entire machine? Is it a thread? Is it a process? Is it a virtual machine? Is it a software module? Right? In practice, very often, at least in the case of software, it typically is a library or a software module at which that kind of analysis is done. And so if you think of a typical internet distributed system service, you're going to use GNU TLS for encryption. You're going to use the operating system, which is Linux. I don't know how many lines of code there are in Linux these days, but it's a lot. And many subsystems. All of them, each of them may have 400-year mean time between failures, but the successful execution of your request has to have all of them. Any one of them failing is enough to wipe you out. So this is where the trouble begins, okay? All right. This simple and clean failure model, your goal as a practical matter, I'm going to go through in the next 3 slides, 3 examples, real-world examples of systems that do not have this property. Okay? Just to give you real examples of where it does not work. And at least one of them is personal. I personally experienced that bug. So it's actually useful to know them. But that said, your goal is to build systems that are fail-fast, because then they become building blocks from which it is possible to assemble more complicated systems. Okay? What is this different breed of failures which do not follow this nice property? Right? It's much uglier failures. You get a result, but like 1 + 1 is 3. I don't know. You say get packet, and it gives you a packet, but the bits in the packet may not be what got transmitted. How are you going to write code that deals with this? Okay? This class of failures is referred to as Byzantine failures. It is the opposite of fail fast. So components that are not fail fast are said to be capable of exhibiting Byzantine failures. Okay? So do these kinds of failures really occur in the real world? So let me give you 3 examples, okay? This one is personal. It really happened to me personally. Dates a long time ago, but the bug could have happened today and would still be true. So here's the setting. In the very first deployment of AFS at CMU, it was 1984, I think? Yeah, 84, 85. CMU was a smaller university at that time. There were only 5,000 students. About 10% of them, I believe 500 users, were already using AFS. And we started getting reports that people's files were getting corrupted. I saved my homework, I read it back, and the bits have changed. Not what I saved. I mean, how would you like that? You're working frantically to meet the project deadline, you save a file, you come back a few hours later to continue your homework, and your C file has changed in ways you don't know how they changed or what they changed, right? So, as you can imagine, this was very serious. We spent a lot of time trying to figure out what was going on. Nobody could figure this out. It was definitely true. The only correlation we could find was somehow it was dependent on network load. Before deadlines, remember Murphy? Murphy was at work. Okay? Before deadlines, late in the day, when everyone is trying to get their stuff done and go home, the chances of the bug striking were higher. Guaranteed. Okay? So, based on everything you know from 15 to 13, what would you think the bug is due to? Yes? Race conditions. Perfect. The first instinct of any software developer, programmer, when you see something load dependent, is say, okay, this must be timing related, most likely a race condition that gets triggered more often. We spent weeks carefully going over the code. No race conditions. So what do? Well, I'm compressing order of 4 to 5 person months of work into 5 minutes of class time, okay? So systematically tracked inwards and narrowed the problem down to the Ethernet driver code on the server. Okay? Now this was 1984. You have to understand that Ethernet, which is a wired network protocol in 1984, worked similar to Wi-Fi today. So today's Ethernet is what is called a switched Ethernet, meaning you have a wire directly that connects you, and then there's a box, which is the switch within which the routing of the packets happens. Wi-Fi works differently because all of you are in this room. When his laptop transmits a packet and his laptop is trying to transmit a packet, protocols, like raising your hand, for example, or if you speak and you hear someone else speaking, one of you backs off and stops speaking. Right? So we have developed protocols. So in the Wi-Fi world, and in the Ethernet of 1984, this protocol was referred to as a Media Access Controller, MAC. Okay, it's true today too in Wi-Fi. So this is the code that was responsible for the bug. So all of it. Here's how it worked. You copied a packet to the network interface card, and then there's a loop with a certain number of retries. You tell the network card to transmit the packet. You check the return code. If the return code is success, fantastic. Your packet got out. It's on its way to the destination. But sometimes, just at the moment your card transmitted the packet, someone else's card on the network also transmitted a packet. And that's referred to as a collision. So the return code would tell you if a collision happened. If a collision happened, what you do is you pick a random number, you sleep for that amount of time, and then you go back and you try transmitting the packet again. It's just like asking questions in a room like this. If when she speaks, he also tries to speak, one of the two of them has to stop speaking, the other one continues or speaks first, and then when that person's question is answered, the other person asks their question. That's what this is implementing. And the randomization is just to make sure that we do not have deterministic collisions. Right? So randomization is useful. So what could go wrong with this code? Right? I mean, there's all of it. It turns out this code was working everywhere else perfectly. So it's only on this server. But somehow this code was not working right. What could possibly be different? So it made no sense. So in total desperation, we moved the copy packet from outside the loop to inside the loop. Just on the off chance, maybe there was some kind of race condition that was modifying the bits that had been copied earlier. By copying it again, you're eliminating that race condition. The problem went away. What was the race condition? Turned out there was no race condition. It turned out that the bug was that the hardware in the network interface card was flaky. When you wrote bits into the buffer, the DRAM refresh in it was buggy, and there was some non-zero probability that in a few seconds the bit values would change. So if you copied and then transmitted, that was a very short time, maybe a few tens of milliseconds, no problem. But if you got a collision, you slept for a random amount of time of many seconds, and then you went back and retransmitted, in that time frame, the DRAM refresh may have failed. As a result, the bits you were transmitting were not the bits you thought you copied. The bug fix fixed it because just before transmitting, you again copied the same bit pattern in. Right? The sleep of many seconds no longer intervened between the two. That's it. How do you cope with the fact that there's a piece of hardware that when you copy bits into it, depending on how long you wait, those bits might change? That is the bug here. Right? So this is an example of a bug. Well, thank you. It is 11:30. Perfect timing. But I thought you were celebrating the bug. So this is an example of a Byzantine bug. Okay, and having spent close to 6 months of my life tracking this down, I have learned how important it is to try and avoid these classes of bugs. I'll give you 2 other examples of these class of bugs in the next class, but since it's already said that the class is at an end, it's a good point to end. Okay.